Glycine is one of the 20 amino acids that is used to make proteins in the human body. Glycine is an amino acid, which means it has this amine group where you have nitrogen with 3 hydrogens attached. It's going to be positively charged. You've got this carboxylic acid group where you've got a carbon attached to 2 oxygens. One of those oxygens is attached to a hydrogen. You're always going to have just a straight hydrogen attached to this center carbon where everything else is attached. But this is the only amino acid where this central carbon is not a chiral carbon or an alpha carbon because it's not a stereocenter. The reason it's not a stereocenter, the R group is also hydrogen. So you've got a normal hydrogen and then you've got another hydrogen. And anytime you have 2 of the same attachment on a carbon, it's no longer a stereocenter. So this is an achiral, the achiral amino acid. Glycine. Just like any other amino acid, there's going to be a pH at which glycine has all of the hydrogens on it, and then there's going to be pHs at which it loses some of these hydrogens. The first hydrogen that's going to be lost always from an amino acid comes off of this carboxylic acid group. And for glycine, this hydrogen is lost at a pH of around 2.4. So when you got 2.4, you've got this COO that's now going to carry a negative charge because this oxygen has extra electrons attached to it. This nitrogen still has that 1 extra bond to this hydrogen, so this is still carrying a +1 charge. So because you got the -1 charge here and the +1 charge here, this is considered overall to be a neutral molecule, but there are actual formal charges on the molecule, so that is called a zwitterion, when there are formal charges that balance each other out to neutral, but the molecule still actually has those formal charges. So go up, go up, go up. Hydrogen attached to carbon is always going to be a nonpolar bond, and so this R group is never going to be lost from this carbon. It's always going to stay attached. So as you increase the pH, the only other hydrogen that's going to be lost is from this amine group, this nitrogen, to make it go back to 0. And that hydrogen is going to be lost from this nitrogen at about a pH of 9.8. When the molecules inside the human body or at physiologic pH, which is about 7.4, that hydrogen's still going to be attached to this nitrogen, but it's not going to be attached on this oxygen. So this zwitterionic form, or where you have the negative charge and the positive charge that balance out to overall 0, this is going to be the form that you see most commonly in the human body. So this is what glycine looks like when it's floating around inside your body, a little bit smaller though. Now let's just talk about this R group, aka hydrogen. Hydrogen is not going to be able to create any hydrogen bonds. Hydrogen doesn't have any extra electrons to be able to bond with anything else. It's going to need to take advantage of other electrons from other molecules. But because it's in a nonpolar bond with carbon, it's not even going to have an unequal sharing of electrons within its own molecule. So this is the most simple version of a nonpolar R group that you're going to have. And because this is nonpolar, this also means it's not going to be able to attract water, bind with water, which means it's also hydrophobic. Glycine is not an essential amino acid. You can find other molecules to be able to convert into glycine, including other amino acids. So you do not need to eat glycine in order for it to show up in the human body and to show up in your proteins. One of the really cool things about glycine is that it's also a neurotransmitter. Like, this molecule in and of itself can go and float throughout the human body, bind to a neuron, and create some kind of downward signaling. So glycine can work as an amino acid, but it can also work as a neurotransmitter and help your brain function. So the other cool thing about glycine is that you'll often find it around kinks in protein. So whether that's from the secondary structure or tertiary or quaternary structure, if you've seen a kink in the protein, glycine is probably pretty close because it's so small, it can compact itself around the kink. The big bulky amino acids, so for example, phenylalanine or something that has an aromatic ring with it, those molecules are going to create the kinks. So if you ever have a kink, this glycine is going to come right up next to the kink and cut it down.